In this module on reactions, we are going to look at the final skill set for reactions, which is balancing equations. Balancing equations means that every equation has to follow the law of conservation of mass. And the law of conservation of mass states that matter cannot be created or destroyed. Essentially, what this means is that in the course of a chemical reaction, we have to have the same number and type of atoms on both reactant and product side. We cannot create new atoms. We cannot have things appear. We cannot have things disappear. Everything that is on the product side must be present on the reactant side and vice versa. So let's look at a reaction. Na plus Cl2, sodium plus chlorine. This is a synthesis reaction, and we learned earlier that in that synthesis reaction it would make sodium chloride. So let's look at it on the atomic level. Na could be represented by this purple sphere. So we have one Na on the reactant side. Cl2, the two green spheres joined together, lets us know that we have two Cls. On the product side, we have an NaCl, so there is one sodium and one chlorine. If I look at it the way it is written right now, it does not obey the law of conservation of mass because we have two Cls on the reactant side and only one on the product side. The only way we can remedy this is to add multiples of what we already have on the product side. So I can add a second NaCl. If I do that, I now have two sodiums and two chlorines on the product side. So the chlorines now balance. But now the sodiums don't balance. In order to fix that, I'm going to add one more chlorine on the one more sodium on the reactant side, which gives me a grand number of two sodiums altogether. So if I look at my reaction of two sodiums plus one Cl2 yielding two sodium chlorides, and I look at the representations, both of those have two Nas of the purple spheres and two Cls of the green spheres. They are just arranged in a different arrangement. So this reaction now follows the law of conservation of mass. Let's look at another example. In this case, we have a double displacement reaction, silver nitrate plus iron 3 chloride. So if I look at the silver nitrate, it has double displacement reaction means that the silver nitrate and iron 3 chloride will then make iron 3 nitrate and silver chloride. So I have these things together. One thing I want to note is that both sides of my reaction have NO3 groups. It becomes easier if I balance those NO3s as a group rather than balance the individual nitrogens and oxygens. So that's what I'm going to do. If I look at the reactant side, there is an AgNO3, the greenish Ag, the blue N, and the red O's. So my AgNO3 gives me one silver and one NO3, and I'm going to count the NO3s as a group. The other thing on the reactant side is my FeCl. The bright green chlorine, there are three of them, and the purplish iron. So there is one iron, and there are three chlorines. If I go to the product side, I have the FeNO3-3. So that is a cluster with one iron, the purple thing in the center, and three NO3s around it. And each of those NO3s is the one blue nitrogen and the three red oxygen. So if I look at that, I have one iron, and I have three NO3s. And the other substance on my product side is going to be an AgCl. The AgCl has one silver and one chlorine. So as I look at this reaction, there are not a lot of things that balance. So I want to pick something that I'm going to start balancing with. And in this case, I am going to balance my chlorine. So the only way I can balance the chlorine is I have to have three of those silver chlorides, which now gives me 3 silver and 3 chlorine. So my chlorine's balanced, but now my silvers don't. And the only way I can get my silvers to balance is to put 3 silver nitrates on the reactant side, which now gives me 3 silvers and 3 nitrates. So now if I look at my reaction all together, there are 3 silvers, the darker greenish gray sphere. Both of them have 3 nitrates, which means altogether there are 3 nitrogen and 9 oxygen on each side. Both sides of the reaction has 1 iron, the purplish one, and 3 chlorine, the green one. So the law of conservation mass is now upheld, and my reaction balances. Let's try one more. Iron 3 chloride. In this case, I have the purplish iron and the 3 chlorines again, so there is 1 iron and 3 chlorines on the reactant side. If I only have one reactant, that means it has to be a decomposition reaction. It's a binary compound, so it will break apart into its elements, so it will give us iron. So I have 1 iron, and it will give us chlorine. And remember that elements whose name end in -ene or -gen are going to be diatomic, so chlorine's formula is going to be Cl2. So I get the Cl2 in here, and there are 2 Cl's on the reaction. So now I have to try to balance it. If I try to balance it, I have 3 chlorine on one side, 2 chlorine on the other side, and there is no way to balance that. The only way to get them equal is to find a least common multiple of 6. So to get 6 chlorine on the reactant side, I have to double my iron 3 chloride, which now gives me 2 iron and 6 chlorine. To get 6 chlorine on the product side, I have to have 3 of the Cl2s, which gives me my 6 chlorine. So now everything balances except the iron. To get the iron to balance, I have to add 1 more. And now I have 2 of the purplish irons on each side and 6 of the green chlorines on each side. So this equation is now following the law of conservation of mass, and it is balanced. Next reaction. We have a single displacement. We have aluminum and iron 3 oxide. If you look at the aluminum and iron 3 oxide, we have 1 aluminum, 2 irons, and 3 oxygens all together on the reactant side. As a single displacement reaction, what happens is the element, which is a metal, will replace the metal in the compound. So aluminum and iron 3 oxide will give us iron and aluminum oxide. And if I look at the iron and aluminum oxide, I have 2 aluminum, the yellowish sphere, in my aluminum oxide. I have 3 oxygens, which are the reddish ones, and there's 1 iron altogether total. Now that I've got my chemicals laid out, I can start balancing them. And the things that do not balance in this are the metals, the iron and the aluminum. So if I put 2 aluminum on the reactant side, I now have 2 aluminum, and the aluminum's balanced. And for the iron, if I add an additional iron, so I have 2 iron, now I have 2 iron on each side, so the iron's balanced. So within my reaction, on each side, there are 2 yellow aluminums, there are 2 purple irons, and there are 3 red oxygens. So this now follows the law of conservation of mass, and it's a balanced equation. In this last one, we're going to deal with the combustion reaction. Combustion reaction, C8H18 plus O2. The thing about combustion reactions is combustion reactions tend to be very large. So in this case, combustion reaction, the products are always carbon dioxide and water. In this case, I'm not going to represent it visually. So we're going to get rid of the boxes, and we're just going to work the way I usually work if I have a worksheet, because I don't tend to draw it all out. I look and see what do I have on each side. Each side has carbon, hydrogen, and oxygen. So I'm going to line them up. On the reactant side, I have 8 carbon in the C8H18. On the reactant side, there are 18 hydrogen in the C8H18. And on the reactant side, there are 2 oxygen in the O2. On the product side, the CO2 has 1 carbon. The H2O has 2 oxygen. And all together on this side, there are 2 oxygen in the carbon dioxide and 1 oxygen in the water, so I have 3 oxygen altogether. So this is where I start with. Combustion reactions, it's usually easiest to balance the carbon first. So I have 8 carbon on the reactant side, so I'm going to multiply carbon dioxide by 8, giving me 8 carbon on the product side as well. When I do that, I now get 8 times 2, which is 16 oxygen due to the carbon dioxide plus the 1 from the water, so I have 17 oxygens altogether. Then I want to balance the hydrogen. 18 hydrogen on the reactant side, so I multiply the water by 9, which now gives me 18 hydrogen on the product side. And now I have 8 times 2, which is 16 oxygen in the carbon dioxide still, and 9 oxygen in the water, and 16 and 9 gives me 25 oxygen, so I have 25 oxygen altogether on the product side. If I look at that, there is no way I can get 25 oxygen from an O2. There is an even-odd problem. No matter what number I put in front of my O2, it's going to wind up giving me back an even number. So I'm stuck in a point where I really can't balance it very well. The solution to this is to multiply every coefficient that we already have by 2. So the octane gets a 2. The carbon dioxide becomes 16. The water becomes 18. And this doubles everything we have. So the carbon on each side now becomes 16. The hydrogen on each side now becomes 36. And on the product side, 2 times 16 is 36, plus 18 is 50 oxygen on the product side. And 50 oxygen can be balanced by an O2. Because if I have 25 O2, 25 times 2 now gives me 50. So now my equation follows the law of conservation of mass with 16 carbon, 36 hydrogen, and 50 oxygen on each side. The balancing process holds true for every type of reaction. All reactions can be balanced if the formulas are written correctly. If you should ever hit a situation where you cannot get an equation to balance, what that means is that you wrote one of the chemical formulas wrong. So you should always go back and double check all your chemical formulas, review your notes from your nomenclature unit, make sure the formulas are right, and then go back and rebalance. This ends the module on balancing reactions.